Okay, today we started with the Reynolds transport theorem and we moved directly to thinking about how mass is conserved in an Eulerian reference frame. So the Reynolds transport theorem I'm starting off with here involves the Lagrangian frame for the evolution of some quantity b is converted to an Eulerian frame where we have the evolution of the control volume plus fluxes through the control surface, where this quantity beta is equal to b over m, the fluid mass. So when we think about mass conservation, we say that the quantity B is actually equal to m, the mass of the fluid. And that really simplifies our expression for beta to simply be that beta is equal to 1. So we can, and then the other thing we need in order to write down the momentum or the mass conservation is to say that the time rate of change of the mass of a system, remember a system is just a volume that we're following, time rate of change is equal to 0. And with those two definitions, we can immediately apply the Reynolds transport theorem to define mass conservation as 0 is equal to the time rate of change of the mass of the control volume. Now in lecture I wrote that as a triple integral, I'll leave it in the shorthand here, plus fluxes through the control surfaces of rho times the volumetric flux through each surface. VA being just the volume of fluid crossing the control surface per time. Multiplying that by rho makes it mass per time. Now frequently for mass conservation, we rearrange this expression. Here we have outflows, actually I'll do this in a different color. This expression tells us that outflows minus inflows are what emerge from this dot product. If we move this term to the left-hand side, then we have the form of and switch the sides of the equation. We have the form that we usually use the mass conservation in, so that the time rate of change of the mass of the control volume is equal to minus the sum of the fluxes through the control surfaces, which now the inflows are positive and the outflows are negative. So this is now in minus out. So we have the time rate of change of storage is equal to inflows minus outflows, which is what you sort of expect from mass conservation. The one other case that we talked about was for flow in a closed conduit, where we have flow along this conduit in some way and the area could be changing. Applying mass conservation to this, we reach the result that V, I should note where, let's say this is point 1 and this is point 2. So we say V1 A1 equals V2 A2 equals Q, or Q is a constant along a closed conduit constant density. That was the other specific case that we covered today. So moved quickly from Reynolds transport theorem to the form of mass conservation, which accounts for basically a general case, and then the specific case for a closed conduit, which is given on the bottom here.